not saying that
Okay,
shit.
it's running.
Okay. Okay.
No,
Alright.
no intro?
No intro. Oh, what did I say actually? I just say like, oh.
Well, what is going on?
Okay. Anyway.
Good morning, students.
Okay. So. All right. So today we're gonna go over bonding and electrons, and actually there's two. I was planning on doing two, but we'll see. Anyway, so today we do electrons and what bonding and how the introduction of bonding mechanisms and theories inform all about chemistry. So the first question. So covalent bonds. Covalent bonds. So the important thing about covalent bonds is that at the end of the day, they share electrons. All right, meaning that one atom in the bond is sharing, or there is an equal pull towards that electron. Okay, so for example, a C to a C bond, they're the same atom. Therefore, the electrons are actually equally shared between both of them, right? Where one bond represents two electrons. Now, just to kind of give you a difference, an ionic bond, right? Let's take, for example, Cl and Na. Right? Na and Cl, NaCl, that's where it comes from. Well, the electrons, because Cl is so much more electronegative, Cl is going to have the bulk of the electrons, where Na is going to have a partial positive, right? So covalent bonds share electrons. Ionic bonds, I don't know, I guess they unequally share, or they steal electrons, I guess, is the best way I could say it. But those are just the two big differences between those bonding types, all right? Yeah, and just because I kind of started abruptly, I'll let you guys. But yeah, you guys, I'm gonna kind of how this is gonna work is like I'm gonna try to kind of go through them fast. So if you need me to slow down, just say slow down. All right. Okay, so and then because I'm not looking at you guys, just if you have a question, shout it out. All right. The next one, talking about core electron or valence of core electrons. We're going to abbreviate that versus valence electrons. Right, because this is now a really important chemical concept. Core electrons, they're not associated with binding, or I guess they're not associated with reactions, right? That means that like if you're in the core, right, you as an electron cannot come out to the surface and interact with something else. So you're the core, right? As opposed to valence, the reason why valence is so important, people make a big deal out of it, is because valence electrons, they can react. This is where we see chemical reactions happen at the valence. And so the question reads, are core electrons valence electrons? The answer is obviously no. They're two different things that involve two different processes. Okay. But yeah, so that's why it's important to do valence electrons, because you're going to see when we move on to bonding theories, valence is going to matter. Right? So,
Can you draw it out?
like a valence? Yeah. So let's take, for example, carbon. Carbon has 6 electrons?
It's 4 valence.
4 valence, right?
It's carbon 6, right?
Carbon 6, that's what I was thinking.
Mm-hmm.
Carbon 6, okay. Yeah, I can do that. So we're going to draw in the Bohr's model. So this is my 1s orbital, okay? My 2s orbital, and my 2p orbital. Obviously we know this is not what it looks like, but it's just a really helpful way to kind of look at how electrons are. So remember, 2 electrons per orbital, unless you get into the higher ones. So one electron there, one electron there, fill up the 1s. Another electron here, another electron here, fills up the 2s, and then there's 2 electrons in the 2p. Okay, so the core electrons, obviously as you can see, they're in the core. But the cool thing about this diagram is it also tells you that they can't penetrate out. Right? They're inside, there's a boundary of 2p electrons that keep the 1s and 2s from reacting and stuff. Therefore, that's why they're called the core. And as you can see, the 2p are on the outside. Therefore, those are the things that are going to react, which is obviously important for bonding, which we'll see. Does that make sense?
The outside of the valence.
What's that?
The outside of the
Yes,
valence.
outside is valence, yeah. Or you can even do it as you learn in quantum, where if you have 1s, right, you have the 2 electrons, 2s, and then the 2 p's. The 2 p's. The ones, oops, that's incorrect. The valence electrons here would be this guy, and because they're on the same quantum orbital, they're also technically considered valence. But yeah, you can do it in 2 different ways. Pretty cool. Thank you. Okay, so number 3. All right, number 3. A chemical bond for which one of the bonded atoms provides both electrons for the bond is referred to as a coordinate covalent bond. This is true. Do I have, okay, well, I just say it's true. Yeah, so polar bonds, or yeah, a chemical bond for which one of the bonded atom provides both electrons for the bond. The one I can think of is transition metal ones, but I don't do that one. Well, yeah, okay. So you're going to learn this in 2C. This is the best example I have. Iron. Let's go with NO. So this is an iron NO complex, right? Obviously there's more stuff in there. But a coordinate covalent is that, understand that metals are largely positive, right? Therefore, they don't have an excess of electrons to donate. They're positive, which means they don't have as many electrons as they should. So where do the electrons come from? They have to come from the nitrogen, right? Therefore, you can think of it as like the nitrogen having 2 electrons, and it's donating to the iron, creating a bond, right? And so that's where the bond comes from. It comes only from the nitrogen, because Fe has no excess electrons to give out. Therefore, this is an example of a coordinate covalent. And I think in 2B, I don't think there is an example of this. We'll see. I'll point one out if I see one. Alright, so that's a coordinate covalent where one atom in bond gives both electrons. Okay. All right, cool. So here that's a coordinate covalent. Canaries. All right, so the next one, polar bonds. This is important to get used to the nomenclature, actually. So let's do this. All right, so this is carbon dioxide. Obviously, we haven't, in this, technically, temporally speaking, we haven't learned how to draw this yet. But this is important. So if you have a carbon attached to an oxygen, one of the principal fundamental rules of all atoms is electronegativity. How well are they as attracting electrons? So carbon has one, I think 2.5. And oxygen should be like 3.5. Okay, so These numbers are relative numbers that come from the Pauling electronegativity table. You can find these anywhere. But basically, the higher the number, the more electronegative, okay? So, obviously, oxygen is more electronegative, therefore it wants more electrons, or at least the electrons are more attracted to it, right? And so, what you'll see is chemists will write something like this. It's called a dipole. And in a dipole, that's telling you the direction of the negativity. Where are the electrons going in my structure? And so, like an arrow, right? Where are my electrons going? It's towards my oxygen, because it's more electronegative. Another way, maybe a little easier to think of, is see how I kind of made this little plus sign here? That's where the plus is, the positive one, right? They can also write stuff like this. These notations here, this is a Greek letter, which I don't know which one, but this means partial positive or partial negative, meaning it's not exactly a positive charge or a negative charge, it's a partial one, okay? So it's not formal. But regardless, this is a polar bond, and why, at the end of the day, a polar bond, so this is a polar bond, and the reason it's a polar bond is the two atoms in the bond, so carbon and oxygen, have different electronegativity. So that is the basis of polarity comes from that, the fact that certain electrons are better at pulling certain atoms are better at pulling electrons towards themselves. All right? So obviously, question number 4 is true. Okay. Does that make sense? Okay. Cool. That's polarity. Can I erase? And so we'll learn how to make that carbon dioxide. All right. Question 5. In a Lewis structure, a terminal atom is bonded to 2 or more atoms. All right. How do we want to do this? Do I have a nice way to? Yeah. Okay. I guess I do. All right. So let's take this simple molecule. This is methane. Right, it's an organic chemistry molecule with 1 carbon, where the carbon's valencies are all taken up by the hydrogens. Right, so CH4. Now, as the name suggests, terminal suggests at the end of something, at the end of a chain, for example. At the end of the chain, in this case, I mean, they're all technically terminal, but this guy's terminal, right? Along with all the other H's, they're all terminal. This carbon, though, is not. This carbon is a core. So you have a core atom, which specifically refers to an atom inside a Lewis structure, and then a terminal atom, which is it's an atom on the outside of the structure. And as you can see, this doesn't make a lot of sense, right? Or if so, the question is implying a terminal atom is bonded to 2 or more atoms. Well, it can't be. That wouldn't make it terminal. That'd make it a core, right? So it's the opposite. So number 5 is false, because a terminal, by definition, cannot have more than 1. All right, so hydrogen is a really popular terminal. Okay. So that's.
Wait, when you say 1, you mean 1 bond, right?
Yeah. Oh yeah, 1 bond. 1 bond. Yeah. All right. Number 6. All right, so number 6, in a Lewis structure, each atom typically acquires an outer shell octet of electrons. However, oxygen only acquires 2 outer shell electrons. These 2 things are probably the most important part of this whole worksheet. The idea of an octet. So, 6, spoiler, is true, but why? So let's take a carbon, I guess. Carbon is probably one of the more popular ones. A carbon. And if we draw its orbitals again, 1s, 2s, 2p. Right, so there's the orbital diagram, and as Juan said, there's 4 valence, right? So these obviously are core, right, because they're the 1s. The 2s's, because they're the same principal quantum number, they form part of the valency. Okay. All right. So, as you learned in quantum mechanics, the most atoms prefer to be at the lowest energy. What that means is they want their orbitals to be as full as possible, right? Or at least as distributed as possible. So, to get a full outer shell for a carbon, you need to put 1, 2, and then 3 and 4, right? So those guys, when you actually form a bond, it gets the 4 electrons from other things, which then satisfies its octet. So it's true. So most of the atoms you'll work with in 2B are going to be octet atoms. There are other atoms though, especially after group row 3. So we're talking phosphorus, sulfur, those guys, they actually can go beyond an octet. But for the most part, the ones you'll be working with is carbon, oxygen, nitrogen, they're all group 2. And so group 2s only have an octet, whereas anything below group 3, they can exhibit more. They can have more than 8. And then hydrogen obviously just has a 1s, so it only requires 2. So that's where the hydrogen comes from. I guess for the sake of completeness, hydrogen just has 1s, so it only needs 2 electrons, and then it's happy. It can only do 2 electrons. And so carbon and hydrogen. But yeah, so true. Okay. So number 7, something, was it? The central atom is typically the atom with the highest electronegativity. Right, so this one's also false. And so we can kind of look at it like this. So again, carbon is in the middle. But now this time, let's make it more interesting. Instead of hydrogens, let's make it fluorines. Right, so carbon tetrafluoride. Carbon tetrafluoride, so the electronegativity on carbon, again, I think it was like 2.5. Fluorine, though, is the most electronegative atom on the table with a value of 4.0, right? So obviously, as you can see, we can draw a little dipole, and it tells us that the fluorine, or that tells us that actually the terminal atoms are the ones that are most electronegativity. And that actually makes sense because think of like carbon, if it's positive, right, or it has a partial positive, think of it as like all the electrons are being attracted to the positive center, almost like water bonding, right? How water hydrogen bonds, because it looks for those areas of partial negative or partial positive. So in this case, number 7 is false because it's false, and we see plenty of examples where we have electronegative atoms on the terminal side. All right, cool. And then the final one, so 8, which of the following exhibits covalent bonding? I feel like this is a review from 2A, where you just look at the difference between a molecular compound and an ionic compound. This one should be pretty obvious, where Na and F, again, is ionic, right, because they're charged. Strontium oxide, strontium and oxygen, ionic again. LiH, we have lithium, a metal, and H is a hydride, so in this case, they are actually ionic. And then it's OF2, right, because O and F come from the same side of the periodic table. That is the classical definition of a molecular compound. All right, cool. But yeah, that's gonna be that. All right, so now we can actually get to the Lewis structures. All right. So for number 9, we're gonna be doing a lot of Lewis structures. So I guess now would be a good time to do this. Yep. Okay. All right. So for Lewis structures, what we're doing is we're trying to come up with the most plausible structure of our chemical or of our molecule. Okay. So A is nice and simple. Starts us off with FCl. So fluorine and chlorine together. All right, so how I do this is step one, you want to sum up total valence electrons. Okay? That's step one. Let's just sum up what we have. So we have F and Cl, both are halogens, both belong to the same column, right? How many valence electrons do both of them have? 7, right? So just a quick reminder, the group or the column with boron has 3 valence electrons, carbon has 4 valence electrons, nitrogen 5 electrons, oxygen 6 electrons, halogens 7 electrons, and then noble gases have a full octet, but they still technically have 8 valence electrons. Right? So we have 7 plus 7, right? 7 plus 7, that equals, okay. 7 plus 7 equals 14.
Is helium a special case?
Yes, technically. Yeah, it is. It's kind of like hydrogen actually, because it can only have a 1s. Right? It's a full, or it can only have a 1s. It can't go further than that. Okay, so we have 7 plus 7. Step 2. I think they call it skeleton bond, right? Anyway. Draw skeleton structure. Okay, draw skeleton structure. What that means is you just draw one bond to one atom. Alright? That's it. There's no, don't worry about lone pairs, don't worry about anything, just draw one bond. Alright? So in this case it's really easy. It's just FCl. Right? And now understand that one bond is you using 2 electrons. So what I want you to imagine is that this number from step 1, so the 14 electrons, treat it like a bank account, or a bank balance, an account balance. What you're going to be doing in these subsequent steps is you're going to be taking from the 14 until you have nothing left. Right? So we start off with 14. We just drew one bond. One bond costs us 2 electrons. And so those 2 electrons, we subtract that from 14. So we're left with what? 12 electrons. Okay. Now step 3, fill in lone pairs. Fill in lone pairs on terminal atoms. So in this case, we have 2 terminal atoms. It's a biatomic molecule. So we go over here. There's our initial bond from step 2, and now we fill them in, right, to get the full octet. So fluorine gets 6, right? Because we have 6 lone pairs, and then one bond counts as 2 electrons, so 8 total. And then chlorine, same thing. It's a halogen, so it likes that. Okay? And now we count up. Or we count how many we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now we have 12 electrons that we used up in step 3. So we have 12 electrons, right? That's what we have from step 2. Minus 12 electrons that we just used up for step 3, leaving us with 0. Okay? And that's it. You've just done your Lewis structure. Does that make sense? Yeah. And we'll do like 4 of these. This is an easy example because it's literally just 2 of them. They're pretty relatively easy to understand. Okay. Yeah. Okay. All right. Cool. And I think, when do I introduce formal charges? Oh, okay. Next one. All right. So that's FCl. So we'll keep this step 2, step 3. All right. Next one, a little more complicated. CH3 CHO. Alright. So from here, we want to do the exact same thing. We want to count out our valence, right? So, carbon, like I said, it's a group 4, I think. Therefore, it has 4 valence electrons. Hydrogen, hydrogen needs 2 to fill up, but it only has 1 valence electron. It's 3 times 1 because there's 3 hydrogens, plus another 4 for this carbon, plus another 1 for this hydrogen, and then plus 6 for the last oxygen. Right? So we have 18 electrons. Okay. All right. So now we've got to draw the skeleton structure. So here is where it gets a little tricky because the question I get asked a lot is how do you know what's the core atom and what's the terminal atoms? So there's no real easy answer for this. The best answer that you can give is that typically the terminal ones, both, I guess. The core atoms are typically the ones with high valency. So carbon, boron, stuff that needs things to complete its octet. Whereas stuff like fluorine, chlorine, oxygen even to a certain degree, they have less valency, which means, I shouldn't say that. For terminal atoms, they already have a lot of electrons, so they don't need as many electrons to get their full octet. Therefore, they don't bind to as many things. As opposed to something like carbon that needs 4 to complete its valence, to complete its electrons. It needs a bond of 4 things to do it. Therefore, carbon typically will always be a center, always be a core atom. So in this case, this also is a lesson on reading organic chemistry. So here we see that this carbon here is connected to these 3 hydrogens because they're next to each other. Right? So when you're actually reading a chemical formula, especially in organic chemistry, whatever's next to each other in the sequence is what's connected to each other in real life or in your model. So in this case, we know that this carbon is connected to 3 hydrogens. Okay. And now we're missing 1 valency on the carbon. We're missing a bond. But that can easily be taken up by another carbon. Okay. And then we have a hydrogen connected to this carbon, and then an oxygen. And that's a spoil. Let's just not do that yet. Alright? Yeah. Alright.
With the other carbon, like, it only has 3 bonds, wouldn't that only give it 7 valence electrons instead of 1
Yes. Exactly. So
wouldn't it be a double bond?
which one?
The oxygen?
Yeah, exactly. It would be a double bond. Yeah. It would. But I'm going to introduce the concept of formal charge. But yeah. Eventually, what's going to happen is it'll form a double bond. But how do we get to that point? Right. So now we just drew the skeletal structure. So remember, let's count our bonds. 1, 2, 3, 4, 5, 6. There's 6 bonds. Each bond is worth 2. There's 6. So 12 total electrons, right? So 18 minus 12 electrons gives us 6 electrons left over, okay? All right, and now we take those 6 electrons and give it to a terminal atom. The only terminal atom we have that can accept those 6 electrons is the oxygen, right? So 6 electrons, so 1, 2, 3, 4, 5, 6. Right, so now the 6 electrons are now on the oxygen. Okay. All right, but we're not done. So there is, so as Juan pointed out, if we leave it like this, yeah, our oxygen does have full valency. It's good, but our carbon is not. It's left with, it has 6 electrons, it needs 2. All right, so where do those 2 come from? They have to come from somewhere else that has excess electrons. So they probably will come from the oxygen. But how can you prove that? How do you know that? How do you know that? So, a secret step 4 that in theory you should do all the time, but it's kind of annoying. You want to call, it's called evaluating formal charge. How did I fix that? Evaluating formal charge. Alright, and so formal charge is an easy way to determine whether something in your molecule has a charge. The reason why that's important is because in Lewis structures, you want to minimize charges. So you don't want positive charges, you don't want negative charges, you want to be as neutral as you can be. Alright? So, there's actually a formula that I don't remember often, but valence electrons, that's not the equation. The equation is formal charge, which I'll abbreviate as FC. So formal charge equals the number of valence electrons, okay, minus the quantity of lone pair electrons plus the number of bonding electrons divided by 2. I don't like how this came out, but yeah. So, just to reiterate, the formal charge equals the number of valence electrons minus the quantity of lone pair electrons plus, again, another quantity, the number of bonding electrons divided by 2. Right? So we apply it to things that we think have an excess of electrons. Right? So let's try it out in oxygen. So oxygen, let's see what the formal charge is for oxygen. So number of valence electrons for oxygen is 6. Okay, so 6. Okay, minus lone pair electrons. So there are also 6 lone pair electrons. That's what we put on, right? Plus, how many bonding electrons do we have? Well, we have 2, 1 bond, right? 1 bond is worth 2 electrons. 2, and we divide that 2 by 2, because that's going to represent how many total bonds there are. And that gives us 6 minus 7, negative 1. So that's telling us that our oxygen has a negative 1. Right? And that's actually extremely important. We don't want that. We can also do a formal charge of carbon actually really quick. Just to kind of prove the point here. So formal charge of carbon, in this case, so how many valence electrons are in carbon? 4. Minus. How many lone pairs do you have on this carbon? 0. There's none there. 0. Plus, how many bondings are there? Or how many bonding electrons are there? 1, 2, 3, 4, 5, 6. So 6 divided by 2. What is that? What's that number? 4 minus 3 plus 1. So we actually have a minus charge on our oxygen and a plus charge on our carbon. Right? So when we have that, I hope you guys can see we can take 2 electrons from here and just swing it down. And we get now a double bond. Right? We get a double bond. And then if we do the formal charge calculations again, you'll see that now they're both 0. So 6, let's go for oxygen. 6 minus how many lone pairs? There's 4. Plus how many bonding electrons? There's 1, 2, 3, 4. So it'll be, let's try that. 6 minus 4, right? 1, 2, 3, 4. Plus 1, 2, 3, 4. So 4 divided by 2. So 4 plus 2. So 6 minus 4 plus 2 is 6. So 6 minus 6 equals 0. If we do the same thing for carbon, we'll get 4 minus 0, again, no lone pairs, plus 8 divided by 2 now, because there's 8 electrons total now, and that'll give us 0 again. So this is the whole origin of formal charges and why you can have double bonds, because that's what you want in the end, right? You do not want charges on there. You want to have it as neutral as possible, and that's where that comes from, right? And so eventually, as you do more of these problems, they'll come more naturally to you that you need to do that. But that's where it comes from, and that's why formal charge is so important, because it lets you know what to do. Make sense? Yeah.
Like for the formal charges, can you just add up like the total number of electrons and the bond instead of dividing it by 2?
Maybe do both. This can just be replaced, I think, by just bonds, right? Number of
Yeah,
bonds.
like a number.
Yeah, this can be replaced with normal bonds. All right, cool. All right. Can I read? Awesome. All right, cool. All right, so now that we've done formal charges, now what happens if we can't get rid of the charges in a molecule with formal charges? And that's something called resonance. Right? So a lot of molecules in chemistry actually exhibit resonance. Resonance is actually one of the most important aspects in all of organic chemistry, and in Gen Chem you'll have to know too. All right, so we're going to be looking at this molecule. You've probably seen this one before. That's carbonate. Okay. So what does carbonate look like? All right, so we start off like we've done before, right? Where we count the total number of valence. So carbon, 4 valence. Oxygen is going to be 3 times 6, right? Where one oxygen has 6 valence, so there's 3 of them. But not only that though, the charge adds 2 to our count. That's what the charge means. So if there was a positive charge, you would actually have to subtract the number of electrons. All right? Okay. So we get 18 plus 2, 20 plus 4, 24. So now we have 24 electrons to play around with. Okay. All right. So same thing. We'll do for next step. Draw a skeletal structure, just basic skeletal structure. So carbon, 1 oxygen, 1 oxygen, 1 oxygen. Right. So that's 3 bonds, each bond worth 2 electrons. So that's 6 electrons total. So we do what? 24 minus 6, 18. 18 electrons total. Okay. And now we can fill in the lone pairs on our terminal atoms. Okay. So remember, don't care about formal charge. I mean, if you want to skip ahead, of course you can. This is just, I'm trying to lay down the basic ground rules, but eventually you'll realize that you don't have to necessarily start it every time like this. You'll get used to the pattern. But again, for the sake of the video, we'll trace them all out and give them all lone pairs. Right? So every oxygen gets 6 electrons to fill their octet. Right? And then you notice another thing probably that Juan pointed out, that carbon is missing 2 electrons. So more than likely, we're going to see another double bond, right? One of those oxygens is going to give a double bond. That's eventually is going to happen. That double bond then is going to fulfill the octet of carbon while keeping this oxygen also happy. So they're both happy. But doing it very standardized, it's 6 times 3, that's 18. So eventually we'll see it's going to be 18 electrons minus 18 electrons, so 0 electrons. Right, so we're at step 3, we get 18 electrons. We put 18 electrons. So we have 0 electrons left over. So those are all the electrons we have. They won't come from anywhere else. Right, from here, you can do formal charge calculations to see that carbon, because it only has 6 electrons, that's gonna have a +1, or yeah, +1. And then you'll also see now that each of these oxygens has a -1, right? That's the formal charge of oxygen. Okay, now like we did in the last one, how do you try to neutralize a positive next to an how do you neutralize a positive next to a negative? We'll just take 2 electrons and make a double bond. Right? That'll take away some of that negative from here and give it to here, which is what it wants. So we'll get something like this. Where now this one just has 2, that retains its lone pair with a minus charge. And now the carbon is in plus and so,
What's stopping you from using the other O's?
yeah, exactly. That's resonance. Nothing stops you from doing that. That's exactly what the molecule does. This is just one way, but there's actually 3 different ways that this can distribute. And so it's actually very important for your test because there is a lot of nuance. There's a lot of convention you have to say. So first of all, if you don't put these negative signs, it's wrong. So formal charge has to be explicitly said.
Wait, so every Lewis dot structure, like drawing you make, you have to put the formal charges?
Yeah.
Okay.
There are some, right, like, okay, let's go back to this example really quickly. So if you do the formal charge on both of these guys, it's going to be 0. But you don't have to put 0, 0. It's implied. So only say if it's non-zero. In this case, it's very important you say these 2 are non-zero. Okay? Anyway, but like to Melanie's point, right? You can see that there's 2 alternative options that are equally likely. So you have to put them in brackets because this is called resonance brackets. You have to do a double-headed arrow like this, and then you write out your new one. So I don't know, let's bring it up here. So let's choose, I don't know, this oxygen. That's another resonance form, right? Where we take now, instead of this oxygen giving some electrons to the carbon, we bring this back and we give it to this guy. So now this oxygen forms a double bond. And then we can even do another confirmation, which looks like this, where now it's the other carbon. So these 3 are equally likely, right? But they are all resonance structures of the same compound. And in fact, if you want to be even more precise, I have no idea if they want you to say this or if they expect you to know how to do this, but this is a way to write resonance. The other way to write resonance is to write partial bonds. So if they ask you what does the total look like? Instead of writing 3, that's possible, 3 makes sense, right? You can also write a total Lewis structure, which looks like this. So in this case, again, the C goes in the middle. But notice now that the double bond is what moves. The double bond is what changes, right? So all we gotta do is make the double bonds, we gotta just make them dotted. So they look like this. Which tells us that double bond is moving. And so actually carbonate doesn't look like this at one time. It actually looks like this. It looks like a distributed carbonyl group. And so this is technically now a partial negative, not a full negative anymore. They're actually all partial negatives because the double bond moves around it. Okay. So that's this, and these 3 are the exact same thing. It's just one shorter. One's a shorter notation. Okay.
And will the carbon stay the same, or would it be like a partial positive?
Good question. Let's make that as, yeah, right. Carbon now has a positive in it too. Cool. So this is resonance, and I think for the exam, you do need to include all three, because that's equally light, right? Okay. All right, cool. But these three examples that we went over, the first one being like an introduction to it, the second one now talking about formal charges, and the third one looking at resonance. These are the three main motifs that you're going to see on any sort of Lewis structure, okay? I think, yeah, so that's good. Canaries, you want to go with that? All right, so quickly we're going to go over number 10, because number 10 is interesting. Number 10, I think, is a really good test question. It's a very simple question, but it tests to see if you understood what it means to create a Lewis structure. So number 10 is saying, what is wrong with the following Lewis structure? And it's written like this. Okay. So I hope you can see. Is that really there? Yeah, I guess it's there. I would put it there. All right. There's a few things wrong with this one. But the main thing that's wrong is, do you want to go? Is it?
There's a hydrogen bond, so there's a hydrogen bond in two things.
Yeah. Yeah, exactly. It says hydrogen is specifically only two valency. It can only have two electrons. It can't bond with more things. This is saying that this hydrogen has 1, 2, and 1, 2. It has 4 total electrons. That's not possible. It's impossible. Physically impossible.
But doesn't H also have to be outside because it's a terminal atom?
Yes, but that's because it can only bond with 2. So yes, it also gives the same explanation, but the idea that it can only handle 2 electrons is like the more physical way of saying it. But yes, that's also one way to say it. Okay. Cool. All right. So, one of the things I tried doing for this worksheet, and I was like, oh, I should go over.
That's the only thing that's wrong with it.
The nitrogen looked weird to me. Does the nitrogen look weird? Yes, it does. My bad. Yeah, this is right. Because there's a negative. If you wanted to calculate the formal charge of that nitrogen, I thought that would be a little different, but now it looks next to me. Okay. Interesting. Anyway, all right, so we're only going to do one from number 11. All right, so number 11, yeah, it's fine. All right, number 11 asks us to find the formal charges of the atoms in these structures. So we have to go in and manually label each one, give it a formal charge. So the structure is silicon X. This is silicon, that's fluorine, and it has a 2 minus. Okay, so silicon hexafluorine. All right, so we can use this exact same thing. It's the exact same idea. So first we've got to determine what it looks like before we start determining formal charges. All right, so what does it look like? Oh, bunch of stuff okay, so now we gotta so when we have SiF6, all we gotta do is we have to know what it looks like first, right? So let's count up what its valence electrons look like. So silicon is in the group of carbon. It's in carbon's group, therefore it has the same valence as carbon. So carbon and silicon both have 4. Fluorine, it's a halogen, So all halogens have a 7 on the valency. So total valency is 4 plus 6 times 7, because there's 6 halogens, plus 2 from the 2 minus. Okay, so that's our total valence. So that's what? I have that one here. 48. Okay. We have 48 total. That's a lot. Now we want to draw a base skeletal structure, right? So again, just you can pretend like this is a carbon, right? Silicon is basically a carbon. In fact, people trying to do silicon biochemistry, but that's just an interest of mine. Okay, so silicon's in the middle, right? Because it's a carbon-like. My fluorines. Sure. All right. That's silicon with 6 fluorines attached to it. Okay. All right. So base skeletal structure. We have 6 bonds that we made, so each bond is worth 2. So 12 total electrons. So we do 48 electrons from our total. Subtract 12 now, because that's how much we used. And that's I just can't do math anymore. 36 electrons. Right? Okay, so now we have 36 electrons that we can play around with. All right, so step 3, we want to fill in the lone pairs on the terminals. And halogens have a lot of electrons. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So each fluorine gets 6 electrons, which then, with the 2 electrons from the bond, give it its full octet. Okay. So we did 6 electrons for 6 atoms, so 6 times 6, 36. And we see now that 36 minus 36 is 0. Yeah. I would plug that into a calculator on the test, just to make sure that's a 0. But, okay, so, so we're done. All right, we've used up all of our electrons. Now let's determine formal charge. So, like I was telling Melanie for the previous problem, right?
Wait, don't you gotta draw the bracket with the 2 minus?
Oh.
Wait, how do you?
I mean,
2 minus. Oh.
and we're technically done. But yeah, I mean, yes, you do have to do that. Okay, so yeah, so there's a 2 minus. But the most important part here is to determine the formal charge. What's going on here? So, like I was telling Melanie, we can calculate a formal charge of 1 halogen just to make it clear. All right, so a halogen formal charge. I don't remember this thing. What is formal charge? All right, so formal charge is your valence electrons, which I'm going to abbreviate. Valence electron. Is it minus? Yes, it is. Minus lone pair electrons plus, I don't know, let's do bonds. Let's just make it easy. Plus bonds. Okay. So for 1 fluorine, we have, what's the valence of a fluorine? It should be 7. Okay. Minus, how many lone pair electrons do we have on each fluorine? 6. Plus, how many bonds are connected to that fluorine? 1. So 7 minus 6 plus 1, 0. So what's the formal charge of every fluorine here? 0. But you don't have to write that, obviously, it's implied. But I think the one they really want you to focus on is silicon. Right? So silicon, so what's the valence electron of a silicon? Because it's in the same group as carbon, so it'll be 4. How many lone pairs? 0, there's no lone pairs in there. 4 minus. How many lone pairs? 0. Plus, how many bonds? 6 of them. We get 4 minus 6, -2, and that's where -2 comes from. That's why it has a -2 charge. So in fact, the formal charge on this guy is actually -2, and that actually correlates to the -2 here. That's where that comes from. Cool? Does that make sense? So formal charge is important. It's not an equation you should forget, but yeah, it's right there. Cool? All right. Can I erase? Are we going to do anything? Well, we'll keep it. All right. So that's this. All right. So now we're going to talk about the other ones. Oh, okay. All right. Number 12. In which of the following molecules would you expect the nitrogen to nitrogen bond be the shortest? Cool. All right, so to qualify the statement, I'm going to give you a series. So strongest bond. Okay, so the strongest bond, and over here is going to be the weakest bond. So, let's go strong. So go from your weakest to your strongest. So your strongest bonds are going to be your shortest bonds. Okay? And your strongest bonds are going to be your shortest bonds. Therefore, the weakest bonds are going to be your longest ones. Okay? But what does that mean? How can you tell whether something is long and whether something is short? So your shortest bonds will be your triple bonds. Okay? Where in the middle, like the strong weak bond, is going to be a double bond. And then your weakest bond, obviously, a single bond. Okay? So this series here is extremely important for understanding bond length and bond strength. Will this? I would not be surprised if a question like this was asked on the exam, whether you know how to correlate all these different factors. Okay, and so they ask you though. They ask you a really good question where 12 gives you 5 different options that all contain nitrogen and tell you which one contains the shortest. Which one contains the shortest bond, the shortest nitrogen to nitrogen bond. Okay. But the way you have to figure this out, you have to determine the Lewis structure for all of them and see which one contains the triple, double, and single bonds. Okay. So I'm not gonna belabor the point too much, but the one with the strongest bond, shortest bond, the one that has a triple bond, is this guy. That's N2. N2 will always have a triple bond. This is actually what makes it one of the most stable molecules on the planet. So actually, most of our atmosphere is made out of nitrogen. That's actually why in biochemistry, one of the coolest reactions to ever take place is the breaking of this bond, which is really cool. Okay. N2O4 and N2O. They both have double bonds in them, right? So the nitrogen is actually connected with them through a double bond, both of them. And the last guy, N2H or N2H4, I think. That's a single bond. Oops, I already have single up there. All right, well, but that's kind of what ends up happening. Yeah, that's gonna be it. So that's so that's what N2O4 looks like. What is N2O? that's what N2H4 looks like. So yeah. Anyway, yeah. All right. All right. Anyways. Yeah, one of the things I wanted to do with the worksheet was do this Lewis structure of all of these things. But then I quickly realized that was going to take me hours. But which of the following is least likely to form multiple bonds? It's a good one. All right, so we're going to go back to the whole idea of valency, right? It says our options are what? Phosphorus, oxygen, so P. Do I have it right? Nope. O, N, barium, and carbon. All right, so there's two different explanations. The first, I would say the most difficult explanation here, is actually not that difficult to understand. It's actually what we've been talking about. The idea of valency, right? We know that carbon has four valence electrons, which means it needs 4 electrons to complete its octet, right? So how many different possibilities of 4 can you have? Well, a double bond is 4, right? A triple bond also helps. So there's many different ways that carbon can satisfy its octet. Similarly for oxygen, we saw it can double bond with carbon. Phosphorus, like I said, once you get past group 2, sulfur and phosphorus are the two most common octet violators, right? So they would violate the octet. Okay? Nitrogen, we also just saw nitrogen bonding in a triple bond. So leaving us with barium. So barium is the only one that can't do that. The other way, and probably the easiest way, which could answer this question really quickly, only nonmetals can participate in covalent bonds. And notice that the whole time we've been doing Lewis structures, they only apply to covalent compounds, or molecular compounds, I think they call it. Okay? So barium obviously is an ion. It's a metal, so it can't do that. Okay. Cool. Okay. All right. Okay. Cool. All right. Number 14. They give us a structure CHOH. HCOOH. Oh, that's not formaldehyde. That's wrong. Okay. Well, anyway, HCOOH. All right, like we said, we can do that. Why not? Let's just do that. This is a repeat of what we've been doing. So H has 1 valence, right? Carbon, 4 valence. Oxygen, 6 valence. Oxygen again, 6 valence. Hydrogen, 1 valence. So 1 plus 4, 5, 11, 17, 18. So 18 electrons total. All right. $18 electrons total. Now we just draw a base structure. Notice, like I said, you probably want to ask, okay, which one's the core? Carbon, because it has the highest valency. It needs the most. So it makes sense to go. I see. I see a problem with that statement. Because someone would say, you think like that, right? It's not true. It's not what happens.
Isn't it like electronegativity? Which one's the least electronegative?
Goes in the middle. Yeah. Yeah, that's a definite way to say it. Yeah, that's a good way to say it. I'm just trying to be like, what's the best way to explain why this happened? So, spoiler alert, the H actually goes here. Yeah. So this is something called a carboxylic acid in organic chemistry. It's actually gonna look like that, right? But I'm trying to think of a way to explain why this hydrogen doesn't just bond here.
But why doesn't it?
Yeah, good question. Other than the fact that it just exists, I gotta just trust it. Yeah, I thought it was a formaldehyde. I didn't think it was a carboxylic acid, but regardless, it's a carboxylic acid. Oh, I know how you can tell from the structure it doesn't bond to carbon. That's what we talked about at the beginning. Where is this H?
It's next to.
It's next to the oxygen,
Yeah.
not next to the carbon. So if it was next to the carbon, it'd be like here, I guess. But it's not. All right, cool. It's bonded to that guy. Anyway, if you were to do that, right?
Wait, then why doesn't it bond with the oxygen then?
Yeah, why didn't they like?
Oh, like the oxygen-oxygen bond?
No, like you said, H does not bond with C because it's not next to C, but it's next to O. So why don't you bond it with O?
Like here?
Yeah, like why isn't there a?
Oh, just because organic chemistry, there is an H here, but it's implied. It's implied. But yeah, it's there. It's bonded.
Yeah, but why are the oxygen?
Like combining? Yeah, that's a good question. So the reason why is because this is called a peroxide. That is extremely unstable. That can happen. I work up with a peroxide, but they're super unstable. They don't exist long enough to be a Lewis structure. So that's possible, but that's not, in this case it's not.
But like, how do I know that it's not?
Typically the H's will tell you. So peroxides typically exist with metals. Peroxides exist with metals. If there's H's and a carbon, that's organic chemistry.
Oh, what is it bonds to the one on the right and not the one on the top? The H.
It can. It can do whichever
Okay.
because the whole okay, yeah, so you're right. So
So it can be either one.
yes, but with a condition. So you can have it here, but now this guy is going to be what I call like the naked oxygen.
Yeah, then it's a double
And
bond.
you exactly. So it doesn't matter. This can be the alcohol group, and this can be the double bond, or the opposite. They're equivalent oxygen, right? But the whole point here, right, is that if we were to do this whole thing, you'll see that you'll see a formal charge of -1, and then a positive charge on the C just by looking at formal charge. So what do we do when we see a negative and a positive? We take some lone pair from the negative, put that there.
And to do that, I have to do like all calculations, or can I just like memorize?
Well, you mean you eventually you'll get used to this. This is something that's done all the time, right? But the whole reason I'm doing this is to give you a standardized way that you can just produce, right? But yeah, eventually you'll memorize it. It's pretty easy. Okay, cool. And so then, to kind of sum up the question, we get this called the carboxylic acid. And so I think what it's saying, what was it saying? What are the options here? So 14, the options are the oxygen not also bounded to hydrogen has a double bond to carbon. Okay. Is that the right answer? I hope it's not. I don't know, maybe it is. The carbon has a lone pair, obviously it doesn't. Both oxygens have 2 lone pairs. Actually, yeah, that's true. Yeah, because that still has to have its octet. So it has 2 lone pairs. The OH bond is a single bond. Oh, pick the incorrect statement. Oh, anyway. Okay, so the CH bond is a single bond. The OH bond is a single bond. Both oxygens indeed do have 2 lone pairs. It's B. The carbon does not have a lone pair. It's that's its octet. It's all bonded. Okay.
Wait, why is there 2 and 2 with the H? The one on top, OH. Why does that one have 4?
Why does it have full, or why does it have the lone pairs?
Yeah, that.
The lone pairs?
Yeah.
Well, yeah, I
And
mean,
it's like with hydrogen.
yeah. So let's say let's just take those out, right? Well, I guess first is if you follow this here, right, and you get to step 3 where you fill in the lone pairs for all the terminal ones, you'll see that this one will have stuff because it's
Oh, yeah.
technically terminal, right?
Okay.
But But to your point, let's say we get rid of him. How many electrons are on that guy?
Huh?
How many electrons are on that oxygen if we get rid of lone pairs? There's 1, 2, and then you guys aren't cool yet. You guys can't do that. And then 1, 2, 3, and 4.
I see.
Leaving you with a 4 at. It's a 4. What's the word? Not excess. The opposite. 4 vacancy. 4 deficit. 4 deficit. It's a deficit of 4. And so obviously that's a 4 plus. That can't happen. So you just fill them in with lone pairs.
Oh.
Make sense?
Let's hope.
Well, just know that oxygen, usually oxygen can only bind to 2 because of its valency, remember? They can only have 2 bonds. It can have 3, but then the formal charge will be off. So you always want to see if you can get to neutral. In this case, by having 2 bonds, right, because it has a valence of 6, so how many electrons does it need to get to 8? I think it's 2, right? And so, there you go. Alright, cool. Where's 15? Oh. I was looking at the wrong yeah, so I had it right. Okay, this is called formic acid, but alright. Anyway, stability, okay, so 15. 15, can I erase it? Alright, 15 talks about stability. Alright, so at the end of the day, when you're asked a question about stability and then looking at Lewis structures, you have to understand that stability of Lewis structures, stability is determined on how well a molecule follows octet rule. All right. So it tells you about how close does it follow that rule. All right. So so if you do, or I guess we'll do. Why not? Whatever. We'll do. All right. So what are my options? Ammonia, NH4, CH4. Alright, so we'll kind of go through the options kind of a little quickly, just to kind of see what it looks like. But the first guy you're going to see is ammonia, NH3, right, which looks like N, H, H, H. But we can see that nitrogen doesn't have its octets filled, so lone pair. That's ammonia. We're going to skip B, that's the answer, but we're going to skip it because the other ones are more interesting in my opinion. The next one, SF4. That's not good. Cool. SF4, we see that fluorines all have octets, and then the sulfur has octet too. It's just all bonds, no lone pairs in SF4. CH2F2 looks like this. Alright. Where we have 2 H's and 2 fluorines, and obviously we're going to see that the fluorines have their lone pairs retained. There's an extra in there. Okay. And then the other one is, or the last one is what? Silicon, methyl silicon. Right, where it's Si and then 4 H's. So like I said, silicon Si can be treated like carbon because they're basically on the same group. Okay. And then the last option. The last option is something called nitroglycerin. Nitroglycerin is used as rocket fuel, which is cool. Nitroglycerin looks like this. So it's two N, right? I think it's N2H6, something like that. N2H6. So those H's need to be there. Okay, so this is N2H6. But remember, if we do a formal charge on the nitrogens, if we do a formal charge calculation, we're going to see that this nitrogen actually has a +1, but this one also has a +1. So this is just basic electrostatics. What happens when two like charges are next to each other? They repel, and that's exactly what happens. That's why nitroglycerin is such a good rocket fuel, because it literally just explodes. This is an explosive agent, actually. Yeah, exactly. Okay.
Why do we do that in the labs?
Why don't you? Why can't? Well, you might blow up.
But like, how big is that explosion?
It's enough to power a rocket.
Why can't you put a small
Yeah,
portion
like a
of it,
little
like a little bit?
Yeah, it's
I personally have always wanted to do labs that are kind of cool like that, because I think that's what chemistry is all about at the end of the day.
Yeah.
Because you think you guys right now are just heating stuff in foam cups, aren't you?
Yeah.
That's the whole point.
And then we play with food dye.
Yeah, yeah. I'd make you guys do like a protein project. That'd be kind of cool. Anyway, but yeah, that's 15. All right, let's just keep going. I think the rest of the problems are just it's just structure stuff. Can you draw the structure? Determine the number of single and double bonds. What's the formal charge? Everything seems like we've been covering it. Yeah, I think maybe number 18 would be interesting. Yeah. Okay, cool. Does that make sense? Yeah, it's the whole charge thing, formal charge, structure stuff, that'll all come with practice. That's just one of those things you gotta practice. Can I erase this though? Yeah? Alright.
If something goes beyond an octet, like the one that breaks it,
Uh-huh.
does it mean that it's not stable?
Not necessarily. It typically means it's even more stable. So what you want to look for is the reason why the nitrogen one wasn't stable is because nitrogen cannot afford to have more octets. It can't. It literally stops at 8. But something like sulfur, right, which is a group, it's a row 3 or higher, or sorry, row 3 or lower, that actually can. And so sulfur is more stable just because it can adopt more electrons. But yeah, that's something to look for. All right. I don't know. I feel like they might ask you that question. We'll go over 18 before we go into the next topic, because I feel like number 18 is actually a pretty interesting problem. It's not that difficult, but it's weird. Okay, so number 18 reads, given the listed bond lengths, what would be the most reasonable estimate for the carbon-oxygen bond length in carbon dioxide? So here, you have to determine what carbon dioxide looks like. And so that actually goes back to what we did in the beginning. Right, that's what carbon dioxide looks like. Right, if you do a Lewis stock structure of carbon dioxide, that's what it looks like. Okay, so, but a few other things we got to worry about. One, okay, so they give us a few interesting options. They give us a carbon-carbon bond of 154 picometers. They give us a carbon double bond at 120 picometers. They give us an O single bond O at 145 picometers. And then O double bond O at 121 picometers. Okay, that's all we'll cover for right now, because there's another part to that. All right, so single bond carbon, double bond carbon. Your role at this point is to look at the difference. Right, we don't care about these actual values, we care about the difference between the values, because that tells us how much energy or how much the length decreases when you add a double bond. So in this case, the difference, please tell me how you remember. Yeah, it's 34 picometers. Right, and the difference between these two is 24 picometers. Okay. All right. So now, the other number they give us is the CO single bond, which is 143. So what we have to do now is basically take the two differences we found for the C double bond and the O double bond, and we have to take these differences, specifically take this difference. The reason why we only want this difference is because there's two oxygens, so oxygen dominates, right? But we take this difference and we look at the pattern. We see that a single bond is usually higher than a double bond. So same thing, if we want a C double bond O, which is what we want, we do 143, which is a large number, minus 24. And the only reason why you do minus 24 and not minus 34 is because there's two oxygens, so oxygen is dominating. So you do 134, or 143, my bad, 143 minus 24, that's about 119, which I think is option A. Cool. So that's a problem. I think it's a fair question they can ask, but it's a bit it's a bit weird. But yeah, that's a question they can ask. Oh, it's given to you. Okay. So they gave you all these numbers.
Oh, I
You give them. All right. This is a tough chapter. Guys, this is a tough one. Packing a lot. All right. Okay. Cool. But makes sense. So, any questions about formal or anything about Lewis structures that might be weird? Okay. Cool. All right. The next one is arguably the hardest one to explain, in my opinion, because it requires the usage of a few different things. Green or blue? Green or red?
Red.
I agree. All right. Okay. All right. All right. So the next step is we're going to talk about electron and molecular geometry. This is a very important concept as well. You'll see it come back in 2C. Basically, in all chemistry classes, you'll see this come back. The idea here is that now that you know the shape of a molecule, you can classify it into pretty much 6 different groups, okay? So, electron geometry. Oh, that's nice. Electron geometry. You guys probably miss my fancy pens.
I do.
A lot of people actually like them. I'm starting a trend. Anyway, so electron geometries, they look at distributions of atoms and lone pairs. Oh, okay, atoms and lone pairs. But I wanted to stress the and, so I'll just do this instead. Okay, so they look at both distributions of atoms and lone pairs. Right. That's different when we talk about molecular geometries. Molecular geometries are similar, they're not different, but they have one key component missing. They only look at the distribution of atoms only. Okay, we'll see what that looks like when we actually do an example. But we have electron and molecular geometries. These two words are not the same thing. They represent different things. Yeah. So we'll see what that looks like in a bit. All right. So there is a table that I may have put on Canvas. I'm not sure. Potentially, we'll check at some point. But there's a table in your notebook or in your textbook probably. If not, you guys can just email me. I can provide it. But this is a really important table because it tells you. All right. So from this, there's only 6 electron groups. There's only 6 geometries. Right? Only 6. Right? But from those 6 big groups, according to what molecular geometries your molecule has, it can be, I know it can be a whole bunch of different groups. It can be more than like 12. All right. So, number 19. Oh, I highly recommend you getting the table at some point. I don't know if I can.
This?
Yes, it's that table.
Oh no, wait a minute.
It's that table.
She had the whole thing.
Oh yeah,
Show
no,
the
I,
camera. They're really good notes. Yeah, show it.
I like you just got bullied. You got peer pressure to show me. It says a lot about you. Anyway, does that work?
Yeah, take it in.
Okay, so yeah, so this table here is actually really
You know it's
important.
background that camera.
Oh, it is?
Yeah, I think it's from this or no? No, no. Oh, looks fine.
Yeah, okay, but yeah, this is,
Pause and screenshot.
there's that. Okay, so, yeah, and so, let's see, where is it going to be? I definitely lost that. All right. Oh, it's on my Gmail. That's weird. Okay. Anyway, so 19 asks which of the following electron group geometries could have a molecular geometry that is bent. And so if you look at the table, it's actually really easy. But what did I say? Okay. So I said D, so B and C. Yeah. All right. So for 19, it's gonna be kind of hard to explain. Okay, for 19, it's asking which ones have a bent molecular geometry. So like I said, we have 6 groups of electron geometries, but those 6 groups can then be divided into subcategories based on what molecular geometry they have. And so when you're talking about a bent molecule, bent only applies to molecular geometries, okay? And so from the 3 options, they give you 5 options, but they only really give you 3. They're asking out of octahedral, trigonal planar was the other one? Yep, triplanar, trigonal planar, and then tetrahedral. Okay, so you have these 3 options, and then you can have a mix of them. But, all right, so these 3 are electron geometry. Right? These are 3 of the 6. For octahedral, you need to have 6. I'm going to call them 6. We'll call them 6 groups. What this implies is that this can have either 6 atoms or a mixture of atoms and lone pairs. You just need to have 6 regions. And so what it looks like a diamond. So I'm going to say this is the center, so middle. There's there's a group up here which we can label as, I think O would be okay. O, not oxygen. This is just to kind of look at the geometry. So there's one going on top. There's one going on top. There's one going below. And then there's a guy, and then there's the one that forms like a box around you. So this dashed line represents going backwards, and then this solid wedge means going in front of you. So if I were to act this out, these ones are the ones going in front of you, these are the ones going behind you, this is the one going above, and this is the one going below. So it looks like an octahedron. It looks like a crystal actually. It's cool. So that's an octahedral shape. A trigonal planar, you have a middle guy here, and you have one on top, one to 120 degrees, and the other one 120 degrees. Okay, so it looks like a triangle. That's what trigonal. It looks like a chip. What chip has like a triangle? I don't know. Doritos. It looks like a Dorito chip. And then tetrahedral is annoying, but this one looks like a tetrahedron, where you have one going 109.5 degrees this way, another one going 195 this way, one going 195 this way, and one having 195 this way. So it looks like a weird little tetrahedron, but it looks like this. And so as you can see that the four groups here, what they have in, the thing that's you should make a note of is that they have different groups, right? This one only has 3 atoms attached to the middle. Tetrahedral only has 4 atoms attached to the middle. Octahedral has 6 atoms attached to the middle. All right, so number 19 is asking, which of these guys can be bent? Bent, of course, applies to molecular geometries. So bent looks like this, where typically there's lone pairs up here. Okay. In fact, one of the most common bent molecules is water. Water's bent. Okay, but as you can see, trigonal planar is easy to make it bent. All you got to do is take off this guy, put a lone pair. So trigonal planar can, and tetrahedral, that's literally water. So in tetrahedral, you usually eliminate 2 of these atoms, you put lone pairs, that's bent. Octahedral, though, it's much different. At that point, the reason why you can't have bent in octahedral is because you're removing 4 atoms, putting 4 lone pairs, that's 8 electrons. 8 electrons as lone pairs will never happen. They'll react. So octahedral obviously is the only one that can't form bent, where trigonal planar and tetrahedral can. The only other one that can form bent is something called trigonal bipyramidal. Bipyramidal. That's nice, but bipyramidal. Where you have 3 lone pairs. So these are the only 3 that can have bents. All other ones need to be something else. Cool? All right.
When
Okay.
you draw the wedges and dashes, how do you look at it correctly to draw it? Because like, there's 2, like for trigonal planar, you're drawing it like, or like, yeah, you're drawing it like this, but what's stopping you from drawing?
Nothing. It's the whole idea is that the reason why you have wedges and dashes is because you're indicating where you are. So a way you could actually, let's take this guy for example, right? Tetrahedral, how I've kind of done it is like the square is in front of me, right? The square kind of in front of me and behind me, and I have 2 going up and down. The other way you can draw it is what if we rotate it like this?
I see.
And if we rotate it like this, now we still have the middle, but now we have a plane that is not represented by anything specific, as it's a plane, right? So we went from here. The plane was like this, on like a hula hoop, like that, right? And then we rotated it. Now the plane's on the plane of the board. But now we only have, now the thing that was on top is now behind us. And the thing that was below is now in front of us. Right, so it doesn't matter so long as you're consistent. So long as you use the convention that chemists have come up with. Yeah. Cool. All right. Number 20, this is actually a classic Chem 2B problem. They're going to give you a molecule. You have to draw the Lewis structure, and from the Lewis structure, you determine what it is. All right. So, what is the correct molecular geometry for the carbon atom in urea? All right. So, well, that's number 20. Urea is NH2CO. NH2CO. All right, so when you do NH2CO, right? If we follow this along, actually this is kind of a clue. So it tells you that these 2 H's are attached to this. There has to be a 2 down there. There has to be. Yes, that's what I thought. There's 2 2's in there. All right. Okay, so this should tell you that we have 2 groups of NH2 attached to the carbon. It's going to look like this. and then an oxygen, right? And you know, based on like kind of what Brianna was saying, see single bond O, that usually doesn't happen unless you have an H here, which we don't have. So this will actually have a formal charge of negative, this will have a formal charge of positive. How do you neutralize that? You make a double bond. So indeed, urea looks like this. Urea is actually a really interesting denaturant. Really, it's a really cool molecule. Anyway, so what does this look like? What shape does this look like? Let's look at the Rita. That's a trigonal planar, right? And so when you're talking about groups, right? When I mention groups, a group can be a double bond. This isn't two groups. This is one group. It's just one region, right? And so you have three regions. You have this region, that one, and that one. That looks like a trigonal plane. And that's right. Yeah. All right. 21 just has a whole bunch of stuff. 21 is just coming up with 5 different Lewis structures. Okay, so, but does this make sense? So for 21, I'm gonna just draw the Lewis structures, kind of try to explain a little bit, but we'll just name it. But here at this point, we're not trying to practice Lewis structures. Obviously, you should practice how to draw them. But now we're just trying to label what the shape is. Okay, so, can I erase this? So, 21. I think I messed up this board.
This is very right there.
I guess. I find it boring about it. All right. 21. Okay. So the first one, PCl3. Actually, it looks like a pretty nice one. If you do everything correctly, you should get something that looks like this. All right, so the electron geometry. Remember, for electron geometry, I'm gonna abbreviate it as EG. Electron geometry, we look at everything. We look at atoms and lone pairs. So how many groups are there? Exactly. We have 1, 2, 3, and 4. Okay, there's 4 groups. So they only have 6 options. Which one's the one with 4? This one's tetrahedral. Tetrahedral. Okay, but now what's the molecular geometry?
Trigonal something pyramid thing.
Not that one.
No, trigonal pyramid.
Yeah, trigonal. It's the one without the bi.
Trigonal
Yeah.
planar.
Trigonal pyramidal.
Pyramid.
Yeah. And you can actually see if you do this one, because it's going to look like this. So imagine the double bond is like the peak of the pyramid. So P in the center, and then Cl, and then there's a Cl in front of you. And double bonds right here on top. It looks like a pyramid.
Oh.
Anyway, pyramid.
Okay.
But yeah, so the molecular geometry, because this is something on the table, it has 3 atom groups and 1 lone pair group. This is a trigonal pyramidal. Pyramidal. All right. Does that make sense? All right. Tetrahedral is very common. You should see that a lot. This one's kind of a weird one. Alright, so this is the next one. This is sulfate. So you've been seeing sulfate since 2A, and now you finally know what it looks like. The reason why you can do this, one, is because sulfur is a group 3, so you can actually expand the octet. But we have to know, wait, why aren't we making 4 or something? Why don't we just make 4 double bonds and make it totally neutral? The reason is the charge. So you use the chart to tell you how many negatives you should have. So you're left with 2 negatives. So you can make 4. It's just not according to the formula. Okay? Or the opposite is true. Right? You see this, the formula is negative 2. All right. And so in this case, again, exactly. I just want to make sure that okay. Again, we see how many groups? 1, 2, 3, 4. 4 groups. This is again tetrahedron.
Wait, why is it not fun?
Where's the 5th one?
In the middle. Didn't you do that for the last one?
Because there was lone pairs.
There's no what?
There was lone pairs in the last one.
Oh.
There's nothing.
Oh, I see.
Yep. Okay, so in this case, the both molecular and electron, because there are no lone pairs, they're both tetrahedral. Both of them are tetrahedral. Okay, 4 groups. All right. Okay. The next one is also tetrahedral, so we're not going to do that one. But we'll do the next one. Is that one not tetrahedral? Yeah, that was not tetrahedral. All right, 21D. This is actually what we're learning in 2C right now. Or this is what they'll be tested on. ICL3. What does that look like? Okay, how many groups are there? There's 5. There's 1, 2, 3, 4, and 5. Has 2 pairs of lone pairs. Okay? So the electron geometry, this is trigonal bipyramidal. Trigonal bipyramidal. But now the molecular geometry is actually pretty different. Right? In molecular geometry, we have 3 groups that are atoms, 2 groups that are lone pairs. What does that look like? That is something called a T-shape. Trigonal bipyramidal is the only one that can have a T-shape, and you can actually see the T. That's T-shape. There's also another variation called the seesaw, which has 4 groups, 1 lone pair group. So let's just say, for example, this was a CL instead. This is called seesaw, and it's because it has like a seesaw function, right? There's like 2 CLs on the far right. They're kind of like that's a seesaw. But those 2 only exist with trigonal bipyramidal. Okay. Okay. The next one's actually a seesaw. The next one is BRF4 plus, and that actually exists like this. That is trigonal bipyramidal again because there's 5 groups. But this time there's 4 atoms and 1 lone pair. So that's actually not T-shaped. That's what we talked about at seesaw.
How would you, if you were to draw a seesaw for like with the wedges and dashes, how would you represent?
For me, the easiest way would be
Wait, which way would you look at it? As a writer or as like
whichever one.
the person looking at it?
I like to look at it as a person who's looking at
Looking at it, so from
it. Yeah, so if I can see it in front of
see
me.
it like this
Yeah.
instead of like this.
Yeah. Yeah. I mean, they're both gonna be the same.
Yeah. Well, can you like for wedges and dashes? Can you draw it in like the rider perspective? Like if you were riding on a seesaw, you're seeing it like
Oh,
this.
riding it on the seesaw.
If you're seeing it like this, can you draw it like
Wait,
that?
are we supposed to know how to do,
Custom?
like, draw the?
Kind of. Yeah, I can do that. Yeah. Okay. Yes, you should. I don't know if it's expected. That might be something to ask. But it should be. Yeah, you should be able to. Okay, so if you're a rider on the seesaw, you'd have something going in front of you. So you'd have a You have an F going in front of you, an F behind you.
Would it be the other way around? Because
It's
you're
the
writing
same
it. You're
thing.
writing it so it's in front of you. So it should the F should be going this way, no?
Yes.
I get what you mean. Yeah.
Because
But you can-
you're writing it, you're just pointing towards you. So shouldn't that F be on this side? Like the F on the bottom be?
Are you?
Oh,
upright
I
now?
see.
'Cause
So,
it's
okay,
pointing
so
in
you're
front of
saying
me.
this is the fulcrum point, and the seesaw you're writing is like this, with the other side empty. That's the fulcrum point.
You're writing it, right? So
You're just
sitting
exposing me. I
on
haven't
it.
written the seesaw in like years.
You're sitting on it. So
Okay.
this side, like this,
Uh-huh.
it's pointing towards you. So shouldn't
I-
that be on the bottom?
I mean, yeah, we can do that.
Does it really matter? Why is it such a big deal to you?
No. Cause doesn't that mean like it's pointing towards you? So like, I don't know. It doesn't make sense. to me
Yeah,
to
so,
be
so okay, fine. If it points towards you, that one's away from you.
Okay.
And then you'd have one F on the sides,
Uh-huh.
and then you'd have your lone pair on top of the fulcrum. So I guess to you it would look like it's going up. So there's no need to draw anything there.
So that's technically right, right?
Where do those lumpers come
Oh, because if you do the Lewis structure, you can see the lone pairs.
from?
But the lone pairs, actually, you can write lone pairs as like a dash or a hash, depending on what you want. But in this case, because you're looking up, they're just straight up.
Doesn't matter where you put the lone pair.
No. Cool. Yeah, but you can draw both. If you do it my way, it would actually also be the same thing. Because there's just two F's that are.
Yeah.
Yeah. All right. Okay. Okay.
What if I told you it wasn't recording? Just kidding. It's recording. What would you?
Well, I mean, it wouldn't be that big. It's on you guys at that point. All right. Anyways, with that, okay. Cool, man. All right. All right. And the last, well, not last. Let's not pretend. This is just a long one. I think this will be long. Okay. For 22, it's asking us what's different or what's the bent one? Yeah, which one's the bent one? So, all the ones, or all your options look like this. There's carbon dioxide. There's carbon disulfide. This is what beryllium F. And then xenon F. So these are all linear. You'll actually do, if you do the Lewis structure, you'll see all of these are linear. And then the other option they give you is water. Water is the most famous bent molecule. Water's bent. 22. Oh, okay, interesting. Oh, I know why I didn't do 23. 23 is just, it was just too much work for me to do, so there's just no way. But 23, 24, 25 are all about resonance structures. It's important that we do 23. I guess I did do 23. Anyway. Alright, 23, the only real reason now that we get to the whole idea of resonance and why resonance is important is because we can calculate something called the bond order. Okay. Okay, so from number 23, which of the following requires a resonance structure? If you do everything, what you'll come up to, what you'll determine is again, there's carbon dioxide. This one can't have a resonance structure because it's literally the same on both sides. Doesn't matter. And plus, there's no charge. So you're also going to get this guy. OCl. Yes, there's a charge, but can you distribute this charge? No. So this one also doesn't have a resonance structure. The last one, and probably the most important one, is this guy. This is actually nitrate. Nitrate actually does have a few resonance structures. And so this is actually the same. I think we already did this in the Lewis structure portion. Okay, and there's this. Right, and from here we can see that all these can be identical, so we can pick whichever one we want. It'll actually be similar. Right, that's a resonance structure. And then this is a resonance structure. Cool. Right, so it has 3 resonance structures. Okay, so from here, what we want to do is we want to calculate the bond order. Right, bond order is what's important here. Okay. So the bond order, which actually you'll see in the other worksheet, bond order is the total number of bonds divided by the total number of, I call it bond locations. I guess we can call it regions, whatever one we want, but I'll explain what that means. Okay? That's a bond order. A bond order helps determine how strong that bond is. Right? So a bond order of 2 actually belongs to a double bond. A bond order of 3 is a triple bond. We want to calculate the bond order of this resonance to tell us how strong that resonance is. Okay? So we can just pick one. For this case, let's just pick one. We'll pick this guy. Right? So what is the bond order of that resonance bond? So what is the total number of bonds that this has? Well, it has 1, 2, 3, and 4. It has 4 total bonds, right? So the bond order is going to be 4 divided by, and now we want to look at how many bond locations, bond regions, and all that tells us is how many different geographic locations. How do I say this? I guess what I mean is, like, remember how I was saying in the structure stuff, in the Vesper theory stuff, I was saying how, like, a double bond counts as one location because they're both kind of going. Although there's 2 bonds in the double bond, that double bond is just one. It's one area where electrons are delocalized. So similarly here, although this has 4 bonds, so 1, 2, 3, 4, it only has 3 locations. 1, 2, 3. Okay? So that's, I guess, what I mean by locate. I don't know, region, location, whatever, as long as it makes sense. 1, 2, 3. So our bond order is actually 4 divided by 3, which is 1.3. Repeating, I guess. And so what that tells us is that, in fact, these are not single bonds. These are like 1.3 bonds. This tells us that it's slightly stronger than a single bond. 0.3 stronger, actually. Does that make sense? Okay. All right, cool. Can I erase? Everyone good with that? So bond orders will come up in resonance. They're very important. And they will come up in molecular orbital theory. Have you guys touched molecular orbital theory yet? You guys are gonna see that one. All right, you're like on chapter 12.
Yeah.
Okay.
Wait, if you have resonance structures, don't you calculate the average bond order across the whole thing?
Yes, that's the same. I mean, the same idea. That's the whole idea. Is the reason why you want the average is because that'll tell you how strong that resonance is, right? But yeah, cool. All right, the last few things here. We're talking now about polarity. Interesting. It gives you the answers. Farhat never did that. Anyway. So here we want to talk about which bond is most ionic. 26, these are important things. Polarity is probably one of the most important concepts in all of chemistry. I know for sure it is in biochemistry, but 26 talks about what is the most ionic bond here. The most ionic bond, wow, this is a really nice green. Most ionic bonds, or sorry, the most ionic bond is the one with largest difference in electronegativity. So, like I was saying, now that we're talking about ionic bonds and polar covalent bonds and polarity, what now you want to focus on is talking about which one has the largest electronegativity. Right, this is where it comes from. Now here, I don't know if they're going to give you the electronegativity table on an exam. I don't know, but I have a few things here. So these come directly from the table. So these are values directly from the electronegativity table. They come directly from the electronegativity table, and all we're going to do is we're going to take the difference between those numbers. When we're given the options. So, for example, option A is 00, right? But it's all it is. 00 is just 3.5 minus 3.5. That's 0. It's actually probably the least polar bond you can get. It's a bond with itself, right? That's not really polar at all. BCO bond, so that's going to be 3.5 minus 2.5, value of 1. It's pretty good. C, what's C? NaO. This one's 3.5 minus 0.9. This one's huge. This one's 2.6. Okay. LiO is 3.5 minus 1. That's 2.5. And then MgO is 3.5 minus 1.2. And that's going to give us some number 2.3. So just by looking at these numbers, the most ionic is my sodium oxide. Okay. Yeah. Cool.
What does it mean for something to be polar?
Polar?
Yeah.
It literally means is there a difference in electronegativity? But I mean I can give you a little list, I guess. Okay, so yeah, let's do it. So to your point, can I erase this? So to your point, actually we'll keep two of them. We'll keep LiO and then OO. So what constitutes polar? Right? So there's nonpolar. You only have three options. There's nonpolar, polar. Okay, well, let's make this as complete as possible. There's covalent nonpolar, covalent polar, and then ionic. Right? Three options. The question you're trying to ask is, what is the cutoff? You're always trying to, the reason, it all comes down to the difference in electronegativity. That's what tells you whether something is nonpolar, polar, or ionic.
What does it mean to be polar though?
It means that electrons are skewed a certain way. There's more electron density in a certain area. So like remember we can use this one. So typically we know that lithium has a what? Plus charge, right? Oxygen has a -2 charge. So electrons will prefer to be near the oxygen, leaving Li with a partial positive. So that's what polarity means. It just means which one, where, if something is polar, that means that the electrons like to be, the electrons are not equally shared. They're in a certain area. And for example, here they're with the oxygen, because oxygen is more electronegative.
Because it's closer to like a noble gas.
Not close to noble gas. It's because it has the highest value.
Oh.
Yeah. The highest value. Noble gases are not electronegative at all, right? Because they don't have a charge, right? The highest number you can get though is 4.0, fluorine. So if you're closer to fluorine, you're more electronegative. Hmm? Yes. Yeah. But the important part here is where's the cutoffs? You know, what represents nonpolar, what represents polar, and what represents ionic? So for nonpolar, it's 0, a difference of 0. So like 00 to 0.4. So if the difference lies between these two, you're nonpolar. Right? Covalent polar is 0.4 to 2.5. So if your difference is between these two, you're technically polar. You're just polar. Okay. But when does it become an ionic bond? That's when you have 2.5 to 4.0.
Well, what if you have 0.4 or 2.5? How do you know?
Oh, that's kind of, if you have 2.4, you'd probably be a very weak polar. If you're 2.5, you're a weak ionic.
Okay.
But these are the relationships with this. Yeah. Okay. All right. The last few things here I want to kind of cover is, to your point, how do you represent polarity? So dipole moments are important. All right. So can I erase? Does that make sense? All right. Last few things here. I'll look at the dipole moments. 28 is asking. You know what? Let's just do 29. Let's just skip. 29, we can do the exact same thing. Doesn't matter. 29 is asking, which of the following do you expect to be polar? So the first thing they give us, HCN. So first off, you need to do is you need to determine the structure. You determine the structure, and from here you can see a few things. Okay. This is where you kind of need to be familiar with the numbers. So hydrogen has electronegativity of 2.1, carbon 2.5, nitrogen 3.2. Not true? It's 2.0. All right. All right. So going back to what I was talking about here about the cutoffs, right? C and H, right at the you're right at the border. You're 0.4, right? Typically, though, carbon and hydrogen's typically nonpolar. Right? So this is nonpolar. But how about C and N? C and N have a 0.5 difference. So we know now that nitrogen has a partial negative, carbon has a partial positive. Okay. So this is a polar molecule just because it already has a polar. We know that now. But we also want to figure out the dipole moment. The dipole moment, I like to think of it, dipole moment. It answers the question. Where do the electrons go? All right, all you're going to do is draw an arrow, like we did it right at the beginning. Draw an arrow to say, where do the electrons go? So here, they don't go towards hydrogen, they don't go towards carbon, they go towards nitrogen. So what does the dipole moment look like? Okay. Since it's a linear molecule, it's going to be a line an arrow going towards nitrogen, where the tip of the arrow represents a partial negative, and then this little positive sign represents a partial positive. Okay. So overall, what you're saying here is that if I had if I had a molecule of, this is called acetonitrile. If I had a molecule of acetonitrile, and we took it as like a whole, right, like a whole molecule, this side will be the partial negative, and this side will be the partial positive. Which means, where would water interact? Let's say like water came in like this. Right, water itself is a polar molecule, with its dipole moment straight up like that. Right? These two won't interact. Water is going to interact with this side. Or if the water was flipped, where now the hydrogens were aligned with this guy, now the hydrogens would interact with this side, not that side. That's why it's so important, is because it tells you how it's going to react. Does that make sense?
Wait, so that's partial positive?
Here?
Yeah. And I was, wait, the negative sign is the,
What do you mean?
wait, what does the Greek symbol mean again?
It means partial.
Oh, partial?
Yeah. So it's not a full negative. It's like a
Oh.
partial negative. It's an in-between.
Oh.
That's what it's saying.
So it's either partial positive or partial negative?
Exactly. And if you already found out your partial negative, you automatically found your partial positive. It's just the opposite way.
Does partial negative means like it's polar?
Yes.
How do you know like that it's a linear
Linear molecule?
molecule?
Yeah.
Why does it have to be linear?
Yeah, good question. So it's because if you determine the Lewis first, you have to determine the Lewis structure, right?
Right.
So when you get the Lewis structure, you're going to get H, C, N.
Okay.
Right? But you might be asking, okay, so then why isn't it bent, I guess, would be probably another option?
Yeah.
It's because there's no lone pairs in here.
Okay.
The reason why it's bent is because the lone pairs are literally, so this is linear, right?
Mm-hmm.
Now, if I had lone pairs on top, they'd actually be pushing down.
Right.
That's why you get bent.
Okay.
There's no lone pairs, so they're straight. Because the whole reason VSEPR exists is because it's a theory that says, oh, I want to minimize the electrostatic interactions. Right? I want to make it less. I want to give as much distance away from my groups as possible to limit steric hindrances. But does that make sense about the dipole moments? That's what. So a dipole moment is literally this. Where do my electrons go? For water, since the oxygen is the most electronegative, it goes toward the oxygen. Right? Other options. Oh, that's a good one. Okay, how about this guy? Is this pole? Remember, carbon and hydrogens are never polar. This is always being nonpolar, always. That's actually the whole thing about a fat. That's what a fat looks like. That's what oil looks like. This is nonpolar. Therefore, if it's nonpolar, there is no dipole moment. Right? Electrons are equally distributed, relatively speaking. They're equally distributed among everything. So they're all just there. Okay? So there is no dipole moment. Okay? Now this is probably my favorite. Silicon with 4 fluorines. Silicon tetrafluoride. Okay? Alright, so I told you that fluorine is the most electronegative you can get. That's a 4.0 value. Silicon is basically carbon. Actually, it's less electronegative than carbon. It's around 2.1. So these bonds are definitely polar, right? So where do the electrons go? Toward the fluorine. Right? But now the fluorines are all kind of competing with each other because they're all really electronegative. But that's the important part. If I asked you, what is the total dipole moment? Where do the electrons go in this molecule in total, overall?
What's that?
Sure, yeah, but like if I were to ask you which one's the positive side, which one's the negative side, left or right, or top or bottom,
Aren't they the same?
they're all the same.
Yeah.
Everything has the same. Everything is the same, and the way you can look at that is actually I like looking at this mathematically. These dipole moments are actually vectors. Vectors we learn from physics. Physics tells you it's literally an arrow with a direction and magnitude. When you have two vectors that are the same magnitude but opposite sides, they cancel out. So although this molecule has individual dipole moments from Si to F, overall, this molecule is actually nonpolar. because all the polarity cancels each other out.
Can you look at symmetry as well?
Yeah, symmetry. That's actually another way to
Is
look
that
at
a
it.
seesaw?
No, because there's no lone pairs.
Oh, okay.
So there's only 4 groups. So that's just tetrahedral.
Oh, okay.
But so this is a really big concept here. That yes, although you can have individual dipole moments, if I were to ask you the overall dipole moment of this molecule, it's nonpolar. There is no dipole moment.
If there's a lone pair, then is it polar? Because
Yes.
there's no symmetry. Or
So see, this is where it becomes kind of weird. Yes, well, there's symmetry. There is symmetry, but it's polar
that's polar.
because let's say the lone pair is here, right?
Yeah.
Where would you draw that? Where would you draw the arrow? Going up, right?
Go up.
So where's the net dipole moment? Going up.
Going up.
Because these 4 still cancel out, but now there's a negative dipole moment going up.
Oh.
So that actually now makes it polar. Does that make sense?
Yeah. But then if like F becomes like H, then it's polar as well, right? Cause,
Yeah. Because now you've broken the symmetry. Now this vector is going to be smaller than this one, which now means that your net dipole will probably be this way. So dipole moments tell you all about polarity. Hmm?
They made it up.
Actually, yeah, these numbers are all made up. But 4.0? Oh, there we go. It's a relative scale.
Wait, yeah, how did they measure that?
I don't remember. All I know is who it was measured by. Linus Pauling is probably one of the most famous chemists of all time because not only did he win a Nobel Prize for chemistry, he's one of the only other people to win a Nobel Peace Prize. So he won both. So he's a very, very cool guy.
So the numbers are fake.
The numbers don't mean anything real. They're just relative. It's a relative scale. So he determined that fluorine was the most electronegative, and then it went downward like that.
How?
Yeah, I don't know what experiment he did for that. It's physical chemistry stuff. That's annoying. Okay, cool. I think overall, other than that, I think we're pretty good.
You actually taught me more in like a few hours than I actually had in like 2 weeks.
Really?
Yeah.
Good. So that's one video.
Do an outro. An outro.
You do it actually.
No. On for me.
I'll show you.
No, don't turn it.
Like and subscribe.
I'm just gonna.
Bye.
I'm just
My
gonna.
team